so let's now summarize everything and turn it into some principles and some theorems, so as to make everything clear and how we're supposed to proceed to a theorem, which is for maths. Theorem on local extrema, which is what we've been applying to all the other examples, the previous examples. We are just formalizing everything now on local min or max. Okay, so local min or max or local extrema. So these are the extrema of a function f. So what does it say? If f of c is a local min or max, then c is a critical point of the function f. Remember that in order to be for f of c to be a local min or max, c must lie in the interior of the interval. So this does not contradict any of the other observations we've made and the applications we've gone over, where we need to look at the endpoints, because when we're looking for critical points, we're looking for possible maximum or minimum, maximum or minima in the interior of the interval. And by definition, local min and local max are points that are maximum, absolute maximum or minimum, or on an interval that contains the point in the interior. So if you're on an endpoint, then that cannot correspond to local max or local min, because you cannot find an interval around it that contains a point and for which is a local, which is an absolute max, because it will never be in the interior. If you're an endpoint, it's the lower endpoint, that point will not have, you will not be able to find a point on the left of that, point that are still contained in the interval. Okay, so this is why this is just one of the things we've been doing. It's just we didn't summarize it or put it into a theorem. But whenever you have a local min or max, so something that's in the interior of the domain of the function f, and it's a local min or max, then it has to be a critical point. So that means either a point where the derivative is 0, or as in this example that we've used now a number of times, which is the function absolute value. So the absolute value of x in -1, 1 of okay, so if it's so again, -1 and 1 are not so they're the absolute max, the absolute min of the function inside the interval, but they're not local max, because you cannot find an interval here like this, where instead of containing -1 and 1, that lies completely inside the interval -1 and 1. So these are not local min or max. The only local min is actually the global min, which is 0. 0 is a minimizer, the absolute minimizer, and also a local min. In fact, any interval here, any open interval containing 0, so in any such interval, the absolute value of x will have 0 as as an absolute min. So 0 is a local, is a min, and it's also a local min of the absolute value function on -1 and 1, and actually on the whole of R. Okay, so it's a local min, and according to this theorem here, f of c should be no, c then should be a critical point of f. In this other case, yeah, c is a critical point of f because at that point, f prime doesn't exist. So that's one of the ways in which is one way in which C could be a critical point. Okay. C is a critical point if f prime doesn't exist, or if f prime is equal to 0 at that point. Then the theorem, which is just what we've been using, what we've been doing so far in all the applications. So all the applications we've considered so far are applications on closed intervals. So our extreme values on a closed interval. Okay, so we assume now that f is continuous on the interval AB. We're assuming that the interval is closed, so that means that we include the endpoints, because we need to guarantee that minimizers and minimizers exist, and we let f of c be the minimum or maximum of f inside that interval, or maximum value taken by f, value on A comma B. Then what are the alternatives, or what are the candidates for C? C must be either there are two kinds of points that we'll look for. It's either a critical point if it lies in the interior. It's either a critical point where the derivative doesn't exist or where it vanishes. Critical point, or it is one of the endpoints, or one of the endpoints, endpoints A or B, A or B. Okay, so these are the examples that we've, all the examples we've gone over so far involve finding extrema of a function that is defined in a closed interval. The one where we were asked to minimize and maximize sine plus cosine was still on a closed interval. It's just that we were asked to find all critical points. but we were asked to maximize it and minimize it over a closed interval. So what happens now when when we deal with an open interval? What happens when we deal with an open interval? We'll see an example. It will illustrate what happens, okay, in the next video.